So Comic Relief does mainly organize two big campaigns. One of them is Sport Relief, and the other one is Red Nose Day. In sort of 1 year we do one campaign, the other year we do another campaign. And that's our main way in which we fundraise money. So we kind of exist for a brief amount of time in sort of March time, and then we disappear. So this is Sir Lenny Henry, I should say, on stage in one of our main events that we organize. So next year is Red Nose Day in March. We've raised over £1 billion since we started out, so that's a massive amount of money. And when we spend that money in projects we fund all around the world. But what actually people know less about, and so this is a map. It's a really nice map of all the projects we fund around the world. And if you go to the next slide, what people know less about is that actually we fund a lot of projects within the UK as well. About 50% of the money we fundraise is spent in projects within the UK. And we're doing some really exciting stuff about this, but what I'm here to talk about today isn't about how we spend the money, but rather the mechanisms we use to fundraise the money and what technical platform we've built, a serverless platform to help us do so. This is me. I'm Peter. I have no relation to Joe Brandt, who is one of our ambassadors, shall I say, that she did like a crazy thing where she walked from one part of the country in the UK to the other parts of the country, and in the process helped raise awareness around mental health and other issues that are dear to us as an organization. I'm the engineering lead at Comic Relief, which really means that I work with a very talented team, small team of engineers. We're about 10 people. And I'm also a founder at Marzelabs, which is a consulting company from Spain and Portugal. So this is an interactive video. Just imagine it being interactive. About the donation project, the donation platform that I'm talking about here today. So you start by selecting an amount. If you're in doubt, just pick the higher. £150. Click donate now, and you walk through the journey of donation. So it's fairly simple. It's fairly simple to make a donation, but the tricky thing is if many people do so at the same time, you run in all sorts of issues. So I'm here to talk about how we solve this particular challenge. So this is what our donations look like. It's fairly flat. So this is November, December, and then we sort of build up, and we have some type of activity happening in March time, which usually coincide with a radio event, a BBC show in the morning show, or a late evening program that talks about one of the things we're doing. But then actually, it sort of culminates in this massive spike of donations, which coincides with the TV show on BBC One. And that's where we get all our money, in that one single event. So there is absolutely no room for failure. So overview of the talk, I'm going to talk how we architected the system that helps us, get all those donations in. And I'm going to talk a bit how we continuously improve the system. And finally, what we do running this system in production, specifically what are the challenges in a serverless world for us to run this in production. Works? All right, next. So this is the diagram, the architecture of our system. And I by no means copy this and implement this in your organization, because the thing that's of constant change. Don't take pictures. So basically, if the user starts the journey, is going to request the site on donation.comicrelief.com is going to be served the React site from behind CloudFront and from an S3 bucket. And then here is actually where the sort of the serverless magic happens, right? So we got a bunch of functions here, and I'll walk through this in the next slide. So the user starts the journey by calling out to a provider active function. And that provider active function will get you a list of active payment providers. In that case, things like WorldPay, Braintree, PayPal, those payment providers are returned. And we get that list of providers from a parameter store in S3. The reason we do that is at the beginning of the journey is that at any given time, one of those payment providers might have issues processing payments for us. So we need to be able to take one out or load balance between different payment providers at an instance notice. So the change for us to make within the parameter store and reflect this all the way back to the front end takes about 10 seconds. We've tested this under heavy loads. Once the user gets an active provider, the journey starts calling out to a specific payment methods. I think the next one. Yes, so let me talk about how this works. This is the payment method interaction. So this is your Braintree server, so your payment processor. This is your front end. And here are our Lambda functions. So you start out by the front end request a token from the backend that is returned by the Lambda function here. That token is then used subsequently to initialize a payments widget, a secure payments widget that directly communicates with the Braintree server. That is then presented back to the user, and the user is entering their credit card details. We don't handle any of those. We offload this to the payment provider, so we don't have to hold the PCI compliance ourselves. Once that is done, that is processed in the form of a nonce back to a second Lambda function that then passes this on to the backend to actually affect the payment and take the money from your card. So this is sort of a very fast process. Takes maybe 200 milliseconds, but this can take actually up to 2-3 seconds because that's the time it takes to actually take the money from your card. And that's also the weakest link in all of this, which is why we need to build in redundancy with different payment providers. So all those interactions with different payment providers, they generate all types of data, right? Data that we need to use in the backend. We need to use it for our internal data warehousing. We need to use it for our real-time reporting, or we need to use it for sending a thank you email at the end of the journey. So instead of tightly coupling those back to those services, and we talked a lot about this at the conference here, we sort of have a circuit breaker pattern in which we put Sqs in the middle. So we have a Sqs queue here that takes the different messages, passes them onto a delta fan that is then sort of spawning consumer functions to process those messages in batches. We're not directly using SQS's native functionality to spawn Lambda functions right now because we're dealing with FIFO queues, and FIFO queues do not support attaching Lambdas to long poll the queue and launch Lambda functions. But we expect this to change any time, in which case this bit can go, and we can rely on AWS's native support for launching Lambda functions. This is, of course, our weakest link in the system. That's our RDS database. The truth is we actually don't need this. This is really used for reporting purposes only. If this falls down, nothing will happen. The journey will be unaffected. But we still need that because our real-time reporting is built into that. And there's a couple of other applications, not this application, that feed data into the database. So it's not so easy to swap this out with, say, a DynamoDB or any of the other horizontally scalable database solutions. So the main thing when you design an architecture, of course, is to understand the limitation of your components, right? So what are the limitations of your components? I think the next slide. So these are our building blocks. Of course, your Lambda, your compute. Obvious limitation for us is 1,000 concurrent Lambda invocations can happen at the same time. If you actually consider that every payment journey will, on average, call out to 3 Lambda functions in the front, so user-facing Lambdas, and have a couple in the back, it's fairly easy to see that we're going to hit that limit if we're, say, wanting to get 200-300 donations a second. So we lifted that cap with AWS directly. API gateway, obvious limitations is time, 29 seconds for request to timeout. That's not so much of a concern to us because you don't want to have 29 seconds for a user-facing Lambda. Anyways, don't want those Lambdas to run more than 2 seconds max. S3, fairly limitless, although there's also limits with the number of files you can request per second. I think you can have 500 requests per second or something for S3. I'm not too sure about those limits. SQS limits around in-flight messages. You can only have 20,000 messages in flight, so if some of your consumers start breaking down, you might have issues, which is you cannot fully rely on SQS in itself. If your queue is just filling up, or your consumers is taking messages off the queues but actually not acknowledging, so they can be deleted, you might run into all sorts of weird issues, which is you cannot fully rely on SQS. So if you take SQS out of the system here, the donation journey will still work because we rely on S3 as well as an alternative to SQS. And then finally, RDS, quite obvious. Even with the highest instances, you might have only 2,000 to 3,000 connections to your database. That can happen at any same time. So that's why we batch process and batch insert into the database with like batches of 100, 200 different actions at the same time. But actually, the major limitations you have are sitting with your third-party dependencies, right? So you would think none of those would fail, but actually we have evidence that some of those have failed in the past, as recent as, say, last year, where some of those providers, I'm not going to name them out, call them out, but some of those have failures, and they happen. So we need to be prepared for this. So when we're doing this big event on the Friday night, we're actively monitoring each of those individually, and at an instant we can pull one, or we can divert more traffic to one than the other. So we need to be able to take up to 200 donations a second. That's sort of a realistic goal that we're aiming for, which really is quite a large amount of donations. In an hour, that's about 750,000. And all of those donations involve actually taking the money from your card, so we're processing this in a synchronous way. Next thing I want to talk about, so that's sort of the architecture, and next thing I want to talk about is pipelines and how we actually build this system or continuously iterate this system so it's fit for purpose. So in pipelines, you basically have two types of pipelines, and everyone is working probably in pull requests. You got the feature pipelines, which help us to improve the pace of building new features, but also help us catch errors and issues before they start blocking your production pipeline. It's quite important, especially when you work with a varied team of engineers. You're often, not everyone is at the same level technically, so you want to be able to have that feedback loop as early on in the process when actual engineers are building code, and not halfway through when they're actually pushing it to production already. And the most important thing for us is our production pipeline. So all the stuff we do, all the things we build are continuously deployed to production. And this is how our pipeline looks like. And imagine you haven't seen this yet. Has anyone seen this kind of visualizations before? Just 2 people in the room, 3 people. That's actually 4 people. Well, Adam, thank you. So this is a tool called Concourse, and it's fantastic. It's by far the best CI tool out there if you haven't used it. And I'm not too sure why it hasn't been adopted more, but I think the fact that you have to install it and run it on your own server is a big part to it, right? Especially in the serverless, where you want to use managed services as much as you can. But basically, this is the pipeline all the way from your code repository to production on the other side. And you describe your pipeline in code. It's all YAML files. It's really nice to chain up different jobs and have one job block the other job before you move on. And I'm not sure if my slides will work, because this was going to be an interactive video of showing the pipeline. So let's try the next slide. Yes, OK. Well, this is the beginning of the pipeline, right? So we start by running a unit test. Imagine this box now starts pulsating, and a yellow barrier around it, border around it, and starts showing activity. That's when actual code is committed to the master branch, and you start running your unit tests. If you continue this process in the next slide, the second step we do is we do an entire staging deployment. We deploy our infrastructure. Staging, quite obvious, right? Everyone does it. But in serverless, it might be so easy that you deploy directly to production. Well, don't do it. Go through a staging environment first. And we use a serverless framework, so it's literally nothing more than just running this command, right? With a certain deploy environment in a certain AWS region. Once the staging deployment finishes, you move on to the next stage. Yes, here. You start running your tests. And we focus a lot on end-to-end testing. And I'm not sure I have a slide. I think I might have a slide after this. But how many people spend time writing unit tests? Some people. How many people spend time writing integration tests? A bit more, that's good. How many people spend time writing end-to-end tests? All the same people write all the time, all the type of tests. Well, something is wrong maybe, but my point here is spend your time writing end-to-end tests, especially in a serverless world, because end-to-end tests are going to simulate the behavior of your user, more so than if you start writing unit tests. I'm not saying you shouldn't write unit tests, but you're going to get more value out of writing end-to-end tests. End-to-end tests such as user completing an entire brain tree payment, canceling one type of payment and moving on to the next type of payment. Those kind of things. We use a framework called Nightwatch.js that runs on browser stack, which then deploys its own cluster of Selenium instances, which is quite nice. It can be a bit slow, but actually it isn't too bad, especially when you parallelize the jobs. So once we run the entire testing suite on staging, we move on to the next stage, which is a video that won't work. So the next one, which won't work either, but this is it's actually a beautiful slide. Has anyone heard of Cypress.io? No one? It's actually, if you heard of Nightwatch or any other end-to-end test frameworks for Node.js, check out Cypress.io. It's a framework. It works pretty much the same way as Nightwatch does, but it runs in the same event loop as your Node application, which basically means that you don't need Selenium to run your tests, your end-to-end tests. And it's really easy, really fast to run them. You can run them on your Circle CI, your Travis instances, without having to have any external dependencies. And we use this a lot on our pull requests or as part of the pipeline. And the key takeaway here is that you really need to mix and match your testing strategies in order to recreate an entire user experience and catch errors before they go into production. So running this platform in production, right? I mean, what tools do we implement? How do we monitor things? How do we know what's going on? So first thing, and lots of people talking about it, observability. Can we infer the state of the system from different components? Can we actually track a single journey? Can we track a single donation journey all the way through the system? And we started using a tool called IOPipe. Probably many of you have heard of this. Some drawbacks, some positive sides. The positive for us is that we get sort of real-time stats, 2-3 seconds max after a function is invoked. We get sort of invocation counts, errors, those things streamed to their UI. It's quite nice. We get average durations of functions, all those kind of things that can learn us, that can teach us something about the state of the system, right? Some drawbacks are you actually add some latency to your functions. It's about 10-15 milliseconds, which is, in the grand scheme of things, is a trade-off we're willing to make. However, might not work for your use case. Depends on what you're trying to measure here. So one of the nice things here is that you can attach custom metrics. For example, in the Braintree execute function, the one that actually takes the money, we can add a transaction ID. And then we can use the transaction ID on the next slides to do a search. And then we can see other Lambda functions that were used for executing that same transaction. So here we have the create function and the execute function, and we can tie them together with IOPipe. It's really nice for us to get an insight in what's going on. The other thing that's quite useful to us is tracing, so you can look at what's going on within your function. In this case, this execute function does a couple of things. It fetches some configuration from S3. It actually executes the Braintree payment, and then it sends some data to Sqs, right? So we measure all those individual actions. We trace them, and now we know exactly that it took 29 milliseconds to get some data from S3, but it took 2.9 seconds to actually affect the payment. We then put alarms on those, so we can be alerted when there is a degraded service, when we know that Braintree is having issues processing the last payments in the last minute. So we can make an action on this. We can pull Braintree from the pool of payment providers, for example. Another thing we do is crash reporting. So I don't know if anyone has used Sentry before, but it works sort of on the back end and the front end. You just plug it in, and it will stream your errors to your Sentry account, sort of in real time. It's async, so there's no actual hit on your functions or on your front end. And it aggregates errors as well. So you can look at the things that matter most, because in time of stuff is happening, most likely you're going to see thousands of logs that you need to weed through at the same time. So Sentry does the nice thing of sort of surfacing the most important errors to you. And then you can actually also see how many users have been affected by this. So that's something you use in production. And we've learned a couple of things. We haven't used this on the night itself, but we've learned our platform is sort of online or live all year round, and we've learned quite a bit of things from looking at those kind of logs. Next slide. The other thing is Grafana dashboards. Probably many people are using these. We have those around the office, and these give sort of a high-level overview of the status of our application. At the top, you see sort of our front end and how many requests coming in. I took this on an absolute, there was absolutely no traffic going to the site, so it's all 0. It's quite nice. And then we got sort of the status of our pipelines. Is everything passing? Something's blocking, so we can have some engineers look at it and then stack the pipeline if need be. But also things like how many invocations we have on the individual functions, how many messages are in an SQS queue, do we have any dead letters, things that couldn't be processed. So we can look at those. So that just gives us sort of a bird's eye overview of the status of the platform. It's quite useful to us to just understand what's going on. So all those things for us are observability, right? And the next slide. With observability comes alerting. Like you want to be aware that things happen when they happen, not later. So a couple of things that we built on the previous tool. So when warnings errors happen in production, we use Sentry to be alerted of this. When scheduled test fails, so we run a test suite every night as well. So we don't run all the tests all the time for every deployment, simply because that would mean that the test pipeline would run for too long. So we have a series of tests that run in the night that we deem they're not critical for an actual deployment, but we want to be aware of when things happen. And those test things with third-party providers, those kind of stuff. So we use Concourse for this. When user-facing lambdas are over 5 seconds, actually in my updated slide, that's 2 seconds or 3 seconds, because 5 is, is probably on the limit. We use IO pipe for this. It's quite nice. When lambdas are being throttled, CloudWatch alarms. So it's all about setting up the right alarms. That's crucial. And finally, application health checks using things like Warmly, which just pings a status endpoint on your site and checks the status of queues, S3, all the kind of services you depend on. We then stream those to Slack, quite standard, I guess, and then we have possibly a discussion here when things happen or we need to look at stuff. Let's talk about scaling and how we build sort of robust and resilient applications. So, of course, redundancy, the application of critical components in order to increase reliability of your system. In our case, you asked the question before, we just rely on AWS. Yes, that's correct, but we have the multi-region capability, so that gives us a level of redundancy that we're comfortable with at the moment. But also things like redundancy in payment provider. That's probably the most crucial thing for us. We have, for every task, we have maybe 3 payment providers, so 3 different card providers. That if one card provider has an issue, we can swap in and replace with a different one. Then also resiliency, which is the ability to recover quickly from changes in the system. And we've got all sorts of resiliency built in. But actually, rather than me talking through those things, next slide. So we apply something that probably most of you are applying, or at least interested in applying, which is the methodology of chaos engineering. And I went to the microservices conferences last week at Skills Matter, and Russ Miles was keynoting. And for him, chaos engineering is deliberative practice at being wrong. And that sounded so true to me, simply because, how can you assume that your assumptions are correct when you build something? You continuously need to challenge those and continuously need to be better at being wrong in order to improve your system. So it's trying everything, trying all sorts of permutation of the system, really trying to break it is the best way to build a better system, right? And we do lots of experiments with that. So these are some of the things the high-level things, not really in detail, but for example, if our database layer fails, we can fall back to SQS, and we're testing this actively, continuously. If SQS fails, we fall back to S3. If one region or S3 in one region fails, we have the multi-region switch based on Route 53 health checks. If one payment provider fails, we fall back to another one. If the internet is broken, well, you're going to have to use SMS donate or call in to donate. Let's hope this won't happen, but it is a possibility, so you need to be prepared for this. And chaos engineering is about challenging those assumptions continuously within your engineering team, but also with the rest of your stakeholders. We do lots of game days that involve not just our engineering team, but also our stakeholders or different people that are running operations on the night. In the final bit, I had a very nice video again for you to show, but how can you simulate load, right? So I don't know if anyone has done some serverless load testing, but this is probably the coolest application of serverless, or not the coolest, maybe the easiest application to get started, which basically you describe your journey in a YAML load file, and then a bunch of control lambdas are spun up that then each individually generate another bunch of lambdas that are sending load to your system. And then you measure latencies to your endpoints. It's really quite nice. You stream all those things into InfluxDB, and then you display them in Grafana. On the next slide, I got a small screenshot of this. So we simulated 65,000 journeys. Latency, as you can see in the initial part, there's actually quite a big spike in latency, which isn't great, but actually it's mostly the P99s and the P95. So people are affected, but not everyone is affected by this. And this is the cold start that you're seeing. This is AWS trying to spin up a massive amount of a big fleet to deal with your incoming requests. We're working together with AWS as well to sort of get rid of that initial spike, so they can pre-warm a fleet of Lambda cluster for us as well. And then you get your latency graph here, where you can see that on average in this 5-minute period that you simulate loads, you stay mostly below the 1 second. So that's kind of the good thing, but the idea is that you repeat those experiments continuously and combine it with chaos engineering experiments. And that's how you can simulate some sort of real reload on the system. So to end up this presentation, a bit about the serverless mindset that sort of started in Comic Relief. We started about a year and a half ago introducing serverless, initially with a simple use case. We had a contact form on our Drupal website that we rebuilt into a serverless version. Quite easy, but it allowed us to integrate with downstream systems as well, such as a CRM. And actually, we directly saw the value of doing these kind of things. So if you haven't started serverless in your organization, start small is the key to actually, rolling it out across your entire stack. Everything is building block, including your compute. Thinking in that kind of building Legos. I mean, many people use those kind of slides. It's actually quite true, but you need to be, of course, aware of the limitations of your components. You need to continuously challenge those. Focus on managed services. Thank you. Focus on managed services is something that we used to build a lot of things in-house at Comic Relief. We used to spend entire teams, operations teams would build infrastructure for us. We've moved away from this entirely in part due to serverless. Build in observability and alerting. Think about this from the start. Don't add it in the end, because it helps you actually look at your system. And then focus on automation, testing pipelines. It's kind of key in everything we do. Nothing, there's nobody that deploys something for a certain use case. Everything needs to sit in a pipeline. And then finally, deliberately and continuously practice at being wrong is probably the biggest takeaway you can have from this. So thank you very much for your attention.